Okay, come in, sit down. Now, guys, as I said, I haven't given the full 3-hour version of this talk until now, so make your own adventure moment. Do you want me to go into atomics and basically continue talking about memory model, but show you how the memory model manifests itself in atomics, or do you want me to take a break for it and talk about thread safety guarantees first? Which order do you want me to do it?
Atomics.
Atomics. All right, let's talk about atomics. Okay, so C++11, among other things, gave us the stud atomic. So first of all, what's an atomic operation? Atomic operation is an operation that is guaranteed to execute as a single transaction. What it means is other threads will see the state of, in our case, memory, because we're talking about memory model interaction of threads through memory, as either before the operation or after the operation, but not during the operation. So what I mean by that is if you're going to do, for example, I++ or ++I atomically, if you started incrementing it, no other, and if it was 0, and you started to increment it, no other thread will see 0. And if some other thread sees 0, you won't see 0. At the low level, it all boils down to some special hardware instructions. So there is something in hardware that guarantees atomicity at the hardware level. Now, it's not limited to hardware instructions. So for example, you can talk about database which supports atomic transactions, which means if you hit a database with a transaction from 2 threads at the same time, transactions will be atomic. If the record is either inserted or not inserted, but never half-in, so you can't observe it in a half-inserted state. That's obviously done using some kind of lower level synchronization primitives. If you keep going, okay, what's inside those level synchronization primitives, what's inside that, what's inside that, at the end of the day, you will get to hardware atomics. So this is basically what I was talking about. So you do non-atomic increment, both threads read 0, both threads compute 1, both threads write 1. The final result of doing incrementing twice is 1, not what you want. Has to do with the way the caches work, and basically the values that you compute don't go immediately into main memory right away. They're held in various intermediate stages that we don't need to talk about in details. Multiple levels of caches, write buffers, and so on. And they're not synchronized until you explicitly synchronize them. In particular, while you're doing those ++s, if a third thread is coming in and reading it, that thread could actually see your original 0 because neither of those 2 ++s has been committed to main memory yet. On x86, this doesn't happen, but there is hardware on which it does. You're doing an assignment on one thread and reading on the other. You would think that you would either see the value before or the value after. You could see, on some hardware, you could see individual bytes already written and some other bytes not written, what's called byte tearing. Because there are no guarantees that the hardware write itself is atomic. On x86, for ints, there is. For M1, if you're using the SSE types, M128, 128 and higher, then no. You could see half of it being written.
What about with modern ARM hardware?
It has atomic writes up to certain length. I think the latest one would be 64. I'm not positive on 64. Definitely 32. I'm not positive on 64. Now, the atomic, is atomic 64. But if you don't do that, so technically it's UB. In practice, like, would you see byte tearing on 4 bytes? No, I don't know about 8 bytes. All right. So with atomics, as I said, special hardware instruction that basically locks that value in the main memory until all the caches and the write buffers and whatever else it needs to do finish their stuff. So nobody else can access that other thread, no other thread can access that X value until whatever hardware needs to do to commit the value to memory is done. So it's some kind of hardware lock, basically, built into the instruction. You don't individually lock. Usually, there is some hardware on which you do actually use separate instructions. You say, lock that cache line or that value, that address in memory, do my operation, unlock that. On x86, it's built into the instructions, into some instructions. So in C++,
Question back there. So on the atomics, go back one more. Well, the previous slide. Yeah.
okay.
The third thread is reading this. Currently, it's indeterminate whether it will see 0, 1, 2.
It's indeterminate. So so the question is, the question is basically where, like, what happens first. It's not defined what happens first unless you have some other way of determining that. So in fact, it's kind of circular logic. If the third thread came and read 0, we say that it read before. So you need something that it's like, whose clock is faster, yours or mine? Until we compare, we can't answer that question. Unless we compare it to his clock, both of us, then we can answer that question. So the same here. You need some mechanism, which could be that atomic variable or some other atomic variable, to determine what actually happens first and what happens second. Yeah.
At the top of the blue box, should that be atomic int?
Well, it means this one, yeah. Yeah, so we're referring to this end. Yeah. So you're up in the running for the for the calendar. Yeah. Okay, so let's skip through this. So let's talk about stdatomic. What are they for? What can they do? What's the relation to log-free, and what about the performance? Okay. Well, what they are, basically, you can, in C++11, you get the templates to atomic. You can put any type in it, and it becomes atomic. Here is, so all the built-ins don't have to be built-ins. Well, you can't put type with virtual functions. It has to be no except constructor, so it has to be trivially copyable, basically. So it needs to be trivially copyable. We'll see why in a moment. Which means you can copy the bits by memcopy. This is trivially copyable, compiles just fine. Okay, it compiles. What does it do? Well, which operations do they support? They all support assignments, read and write. Always. And then they have some special atomic operations, which are exclusive to atomics. And then they have some operations of the underlying type for certain types. So we'll see that. Okay. First of all, sorry, okay. That I deleted from all the slides because the early compiler that I used had a bug. Constructor was explicit, but it's not. Okay, look at these. One of them is different.
They're all different.
Well, one of them has a fair enough, but one of them has a unique property that the other ones don't have. This one? No.
Assignment to non-atomic.
Well, no, there's only one. There is atomic, right?
Well, no.
Oh, you mean this guy? Okay. Yeah. There's one more.
The y plus 1 is different.
Well,
It's the only one that's not reading from the atomic.
okay, in this sense, yes. But this one doesn't actually compile. Because all of these are atomic operations. And they don't support atomic multiplication, probably because there is no hardware atomic multiplication instruction, at least on x86 and not on ARM. So this isn't, this operator isn't provided by atomic int. It just wouldn't compile. Yeah?
Does that mean there's also no atomic shift?
Yes. Do I have shift? No, I don't have shift. But no, there is.
It would be converted by
But no, there isn't. Yeah. All it has is plus minus. It has the booleans and or. Well, yeah, there is an or equal. So it has the bitwise booleans and the plus minus. Okay, so that one doesn't compile. Two more of these are not the same as the others. Which ones?
The bottom two are wrong.
They're not wrong. However, they're not atomic. So they may be wrong if you expected atomicity. Now this one, okay, we already know that it's not atomic, so no problem. This one is interesting. We're kind of conditioned that this and this and this are doing the same thing. And with atomics, that's not true. This is atomic, this is atomic, this is an atomic read into a non-atomic, like into a register, increment on a register, which has nothing to do with X, and then atomic write, separate atomic write into X. But there was a separate atomic read and atomic write. What happened in between? Whatever you want. Any other thread came in and changed the value between the read and the write. This compiles. You would think that it would do the same thing as this, and it doesn't.
Question.
Yeah?
Why wouldn't the compiler make that transformation for you? In other words, if it did make it atomic, wouldn't that be a strictly substitutable change?
I don't know if that's actually permitted as an optimization.
You could have any expression on the right-hand side.
Yeah, so if for this case, it might be permitted, and I'm not sure if it's permitted. It's definitely not required.
Okay, but if you made that optimization, would you break any program that was relying on there being two separate atomic instructions? I can't think of one.
No, you would not.
Then I would think that would be an okay thing to do.
It would be okay, but unless it's enforced, you can't rely on it, which means you can't count that.
Fair enough.
And of course, for this one, there isn't any equivalent conversion you could do.
Is that explicitly stated in the standard that particular?
It's by exclusion, the other way around. It's stated what's atomic.
One is stated and that one's omitted.
No, it's like these are atomic, everything else isn't.
Got it.
So it's stated by exclusion. The following ones are guaranteed to be atomic, everything else is not guaranteed anything. So it's by exclusion. So this is an atomic read, and after that, this is non-atomic, so whatever. This is an atomic write from some non-atomic stuff. So there wasn't any expectation on this to begin with. Yeah.
Why did the strike through move up one?
Because striped moved. It's supposed to be here.
Okay.
So I guess the line spacing changed at some point. This one doesn't compile. I guess I changed the line spacing between them.
Okay.
I'll move it back. The other two are two separate. The bottom two are two separate atomic instructions. So as we have seen, std_atomic provides operator overloads only for the atomic operations. So star equal isn't atomic and it doesn't compile. That's good. Unfortunately, it also provides things like x equal x plus 1, which compiles, doesn't do the same thing as either of these. And so it's pretty easy to make this mistake. So basically, for that reason, I recommend that you don't use overloaded operators in atomic. I actually don't like that they're even there in the standard, honestly. I would prefer that they weren't there. I'll show you what to use. Okay, so what are other types? So read and write for all built-in and user-defined types. For pointers, increment and decrement, you can put pointers inside. For integers, all the bitwise logic. Yes, question? No? Okay. Sorry? Oh, question, yeah.
In your example, plus equal 1 or plus 1, is there something special about 1?
No. Well, the only thing special about 1 is you have the third alternative, which is plus plus. If you set plus equal 2, plus plus drops out of running, plus equal 2 and x equal x plus 2 are sort of the competitors, and the long one is still non-atomic. Okay, atomic bool is valid. If you're thinking about vector of bool, don't. It's just an atomic of a single byte type. Atomic double is valid, but no arithmetic operations, read and write. No addition, no multiplication, none of that stuff. Until C++20 arrived. And in C++20, we have atomic math on floating points, with the interesting caveat that it doesn't have to produce the same results as the non-atomic math. Because different hardware instruction. Atomic wait and notify that I'll show you in a moment, added in C++20. Okay, that's kind of the operations that are type specific. Portion, subset of those operations is exported through atomic. So atomic of type, if type T supported some like add or assign, atomic of type T supports, may support add if it's an integer. Now there are some atomic, some operations that are specific to atomic itself. Its class, it has member functions. There's load and store. Remember, class is trivially copyable. So it has to, which means it has to be copyable. And now we come to what these actually do. These, at the hardware level, do bitwise copy. That's where the whole trivially copyable restriction is coming from, because it's going to do a bitwise copy at the hardware level. That's just embedded into the definition of atomic. Atomic exchange. X becomes Y. The old value of X is returned atomically, which means if another thread comes in and tries to change X at the same time, you cannot, this transaction cannot be interrupted. So whatever after you exchange, of course, another thread can overwrite your Y, but not during the exchange. This is unconditional. X will always change. Here is the conditional. Very interesting operation. Compare exchange. Ignore the strong for a second. Y is the old value. Z is what you want it to become. If you ignore the Y part, it's just the exchange. But it is a conditional exchange. The exchange only happens if you correctly guessed the current value. So if X contains what you think it contains, then it becomes X replaced by Z, and it returns true. If you didn't guess the current value correctly, then nothing happens to X, and it returns false. And all of that is atomic. The read of X, the comparison with Y, and the replacing with Z, and the returning of the true and false, all of that is single. So if X contains what Y contains, and another thread comes in and just at the wrong moment tries to change X, it will not succeed. It will be held back at the hardware level until you finish writing Z. The interesting thing about that operation is, oh, by the way, that Y is a reference, is passed by reference. And if you fail to guess what the current value of the atomic is, Y is updated with the new value. So if you call it again without changing anything, if you call it again, assuming no other thread did anything in the interim, it's guaranteed to succeed. Because its current value was just exported back to you through Y. If it still sits in Y and no other thread ran for anything interesting, the second one will succeed. Yeah?
These are supported for all trivial T's, right?
It's supported for all T's. No, it's supported for all T's. Well, okay, the object has to be trivially copyable. Trivially copyable. The transaction itself will just does bitwise copy. It will do like memcopy basically.
So my question is there a performance ledge here between whether T fits in a register or not?
Not quite that, but you'll see. You'll see what there is. A slightly different thing. I'll show you. The reason this one is interesting is because it's actually used in most log-free algorithms. So, for example, if we didn't have atomic increment, this is how you implement atomic increment. You read the value, and then you keep trying to replace the old value with the old value plus 1. And if nobody else changed the old value, you succeed in replacing it. And if somebody changed the value, you get the value back, the current value, and you try again. Why would you do that if you had atomic increment? You wouldn't, but you don't have atomic multiply. This is how you do atomic multiply. You read the current value, you try to replace it with twice that. If between the reading and the compare and swap, nobody else changed your value, you succeed. If somebody changed your value, this gets atomically updated to the new value. You try again, in the while loop until you get true. There is a mathematical proof that you can implement any log-free algorithm in this. There is a slight detail in that mathematical proof. It assumes infinite memory. Sorry?
So who doesn't?
Yeah. Okay, you have these guys, basically a member function version of atomic increment. They're supported only for the same types which support plus or plus equal, so integers. They're more verbose. Yeah.
Wait,
So,
fetch add is not quite the same as x plus y because fetch add returns the old value of x.
okay, so yeah. So I didn't do the return value. So yeah, if so there is fetch add and add fetch now. So sorry, there is no add fetch. There is fetch add, and if you want add fetch, you manually subtract.
Okay.
Yeah.
Yeah, you show it correctly on the second.
Yeah, if you want add fetch, you manually subtract the value. Now, by the way, in hardware, if you look at the actual implementation, on some hardware processors, that is the single instruction, and then this one has an extra minus y. So in hardware, it could be swapped. The native could be post increment or pre increment. Depends on the processor. The advantage of them, even though they're much more verbose, is they're much less error prone. If you wanted to write x equal x plus 1, but not using operators, using these, it would be x.load plus 1, x.store of x.load plus 1. It would be obvious that you're doing two separate atomic operations at this point. So for that last reason, that is, people normally read what they want to read, not what's written there, I personally recommend using member functions. Okay, how fast is this stuff? There are some cautions. So first of all, it's kind of meaningless to compare atomic and non-atomic in a sense that if you were in a thread-safe context, you wouldn't be using atomic. And if you aren't in a thread-safe context, then non-atomic performance is meaningless. It produces wrong results. If you want to produce wrong results fast, there are simpler ways to get that, to do that. So okay, if you want to do that and measure, you get something like this. It depends on the hardware quite a lot. So atomic writes, as you can see, atomic writes are pretty slow. Atomic increments are basically the same as writes. Atomic reads, and here you can actually put non-atomic reads, because as long as they're all reads, you're fine. Atomic reads and non-atomic reads, this is done on x86 machine. This x86 CPU with lots of cores on it. So they are fast and scalable. The writes are not scalable. As I said, there is a hardware locking. So at the hardware level, even though multiple threads are trying to do it, at the hardware level, only one of these operations is going at any given time. So it's not going any faster. And it's not designed to go faster. It's atomic. It's supposed to be serialized in hardware. That one operation, but at least it's transactional. It's not. It doesn't give you any undefined behavior. Okay, now the interesting question: are atomic operations faster than logs? Because they both can be used to synchronize access to non-atomic memory. Well, let's look at a simple example. Plus plus. I can do plus plus of a non-atomic integer we'll have to edit it. Okay, well, non-atomic increment, if you do it for multiple threads, the results are undefined. Atomic increment. I have to show you what that. So that P is a pointer to atomic. So increment non-atomic, we don't care about that. Atomic increment. dereferencing the pointer, doing ++ on it. I can do the same thing by fetch add. And I can do the same thing using that mutex right here. And I can do the same thing using compare and swap. Here's my compare and swap loop.
Why a pointer?
There are some. It depends a lot on what the compiler ends up doing. But basically, if you try to do it with a local variable, sometimes you get really weird results. And if you look at the assembly, you see like chunks of code just disappear. So compilers figures out something about that local variable and optimizes something partially. So you get really weird results from the benchmark when that variable is. I don't know why the optimizers work that way, but I've never seen them do it for heap allocated memory. I have no idea why. I just found experimentally that like once in a while I would get something going way faster than it should, and if I look at the assembly, I see that okay, part of what I wanted to do just isn't there. All right, so okay, I'm not interested in writes. I'm not interested in stores. I'm not interested in undefined behavior. I'm interested in this. All right, let's see. Atomic increment, and I'm running it all on 8 threads. Atomic increment, 100 million increments per second. Fetch add, same. Ignore the spin lock for a moment. Mutex, 8. Okay. Who is interested in atomics now? Compare and swap, kind of in between. Having a single atomic is clearly beneficial, but remember, if it was not increment but multiply, the first two wouldn't be an option. Compare and swap still, and the mutex still would be. Okay, so as you can see, a lot slower. So, well, obviously different hardware, 128 threads. So it actually had 128 hardware, 128 cores. A big Haswell processor. Mutex, atomic. An order of magnitude faster. Well, there are more locks or mutexes than stud mutex. So here is the result with a spin log that I wrote myself using atomic operations. Logs don't have to be bad. At least not in the performance sense. There are other problems with logs. Logs don't have to be slow. Yeah.
What are you doing differently? Maybe I've forgotten what the operations are, but
Inside the spin log?
you're doing 170, yeah.
Okay, ask me after. It'll take me like maybe 20 minutes to walk you through what and explain what I can very easily show you what it does. Explaining why it actually helps. That's the. Just ask me after the talk. I'll show you the code.
Are you proposing your lock for the standard?
No, and there are good reasons for that. So I'm not. This is not a talk on lock free. I give a talk on lock free on CppNow a few years ago. So no, there are other so there are other places which are in totally different applications where stud mutex would be much better, and that spin lock would actually be absolutely unsuitable. It's not universally bad. Like in this context, it's very slow. There are reasons for why they've done it that way. Now, kind of to your question about performance and like if does it fit in the word and all that stuff. There is a big secret inside stud atomic. While it's always stud atomic and atomic, it's not always what we call lock free, which means it's not always done by an atomic hardware instruction. I'm just going to show you. sorry, 07 B. Okay, I'll show you this one. Okay, so here is a function that just returns, calls load on atomic of long. And here is a function that calls load on this struct, which has serines. I'm not going to benchmark it. I'll show you the machine code. That thing up there, that's the f of atomic of long. This is what the atomic load translates into for long, right there. This whole mess, oh, sorry, wrong. This is what one little line of atomic load on that struct test translates, and that's with optimization. So yes, there is a difference, big difference. It's still transactional. So it's still transactional. It doesn't guarantee. It's not guaranteed to be lock-free. You can ask either at runtime or starting from C++17 at compile time whether a particular atomic of T is lock-free or not. None of this, like you would think that atomic long is always atomic. Standard doesn't require that. I mean, in practice, yeah, but standard doesn't require it. Atomic flag is the only type which is kind of atomic of bool, basically. It doesn't have to be bool, but it's atomic of something that is equivalent to bool. Yes?
As of C++20, one of the integral types is guaranteed to be lock-free.
But could be the same one as that one.
I'll have to check that. Okay.
This one doesn't say that it has to be bool. It's whatever it uses to store the binary value. Well, of course, I mean, if you know what the underlying type of this is, and you put it here, then that one would also be lock-free. Yeah. Now, what happens if it's not lock-free? Computers basically generate their own exclusion code. How do they? So compilers generate their own exclusion code. How do they do that? They either call this libatomic, which has implementations for it, or they generate these implementations directly in line. Either way, there is usually some kind of little spin lock embedded in this whole thing, and they run a compare and swap loop basically on it, something like that. An interesting question, basically, what happens with the atomic actually? Do they actually wait on each other, like in hardware? And the answer is yes, they do. And now we come to what Michael was asking. Okay, ignore the if-def for a moment. Okay, here is an array of atomic long. And I'm just going to, from multiple threads, I'm going to fetch out of one to the same atomics. Okay, but this is just a benchmark. How would I know if they wait on each other? Well, I need to have something to compare with. Well, I'll compare it with another one where they access different values. Different values, they shouldn't be waiting on each other because they're different values. The C++ memory model guarantees that concurrent accesses to different objects are always thread safe. So the hardware doesn't have to wait if each thread accesses its own array element, even though it's atomic. But I don't have to wait because I'm only accessing, in thread I, I'm only accessing the element I. Here I'm accessing the same element from all threads. Here I'm accessing, each thread is accessing its own element. Okay, we're gonna run that. Okay, this one is shared. Yeah.
When you run these benchmarks, is each thread they're always accessing the same block?
Well, if you put it inside the function, then no. Sorry,
not the same block.
The same atomic in this case. Well, it depends on how you write it. See, the function is called on the thread. So the stack is per thread. This is file static, or file global. There is only one of these. So if you access this, yeah, it's the same, and you didn't put thread local in front of it, then yes, it's the same memory location. Whatever you write here, so this I is different for every thread. It's on the stack, like any other function. You know, even if you didn't call them on the threads, it would still be per stack. Yeah.
Can the array itself be
I
atomic?
don't know. We'll have to try and find out. I don't know off the top of my head, sorry. If you put them in a struct, for sure. Without it, I don't know. Okay. So, so there was a third case which we didn't look at. And the third case was... Okay, so, all right, well, first of all, ignore the circles for a moment. This is what we did. So this is where they all access A sub 0, and this is where they access A sub I. And even though they're accessing different elements of the array, as you can see, it actually doesn't look any faster. So you would think that all atomics on the entire system wait for each other, even though they're accessing different variables. That's actually not true. We got that measurement, and we arrived to this conclusion because there was an artifact in our experiment. And here is another experiment. They're reading A sub I, but the I's are not 0, 1, 2. They're basically, they have a bigger stride, whatever that number is here. So it's like 1, so 0, 8, 16, and so on, yes.
So you're hitting different atomic units in the cache.
Yes, so yeah, that's what I'm going to explain, yeah. So I'll explain to you what that magic number is. But basically, I'm hitting elements of the array that are spaced far enough. And if I make far enough to be enough, I now get scaling where I can actually see that different atomics access, when multiple threads with atomics access different memory locations, it does go faster. So this actually proves, first of all, it proves that when they access the same memory location, they do wait on each other. Here they are waiting on each other. They're running serially, as you can see. When they're accessing different memory locations, they're not waiting on each other. And when they're accessing adjacent memory locations, something weird is going on. Something weird has to do with the fact that even though the CPUs and the registers operate on these things called words, the cache operates on a bigger, like cache word, which is called cache line. 64 bytes on x86. The discreteness of the locking of the cache line, of the cache is at the cache line level. If you want to acquire a hardware lock on a cache, you're locking 64 bytes at a time. You can't lock any less. If you lock the entire cache line, your thread is the only one that has access. Everybody else does not get access to that cache line, period. So that was the problem with writing into elements 0, 1, 2, 3. Even though they are not at the same memory location, they are at the same cache line. Which means when you're writing into an element 0, you're actually locking elements 1 and 2 and up to 8 from being accessed by any other thread. Now, one interesting thing is you actually don't have to be atomic for this. If you weren't writing atomically, this would still happen to you. That's basically, that's just at the hardware level. There is no other way to write x sub 0 except take this entire line, move it into cache, update x sub 0, and move it back. And obviously, when you move it back, you would obliterate x sub 1, unless you kept everybody else from changing x sub 1 while you're doing it. So this happens at the hardware level. Atomic operations do wait on each other, only if they change it. Yes? Okay, I'm getting there. The read atomic operations don't wait on each other, only the writes do. If you're accessing memory locations that are too close, you get into this false sharing situation where even though they're different words, and from the point of view of the CPU core, they have nothing to do with each other, the cache doesn't have enough granularity to give you the locking that you need. It locks both values at the same time. On NUMA machines, which you may even have another kind of penalty, not as severe as this, but for accessing the same page from two separate sockets, so NUMA domains. Because you would be bouncing the entire page between memory banks. Okay, so before we go there, let me show you what the magic number is. So magic number is the size of the cache line. Until C++ 17, you had to know what that is. In C++ 17, in the standard, you get these two numbers. And the one we're actually interested in is this hardware destructive interference size. That's the number, that's the distance in bytes. If you're closer than this, you will have destructive interference, meaning accessing one of the variables will lock the other one from being accessed. Yeah.
Don't you mean that that's the guaranteed distance? If you happen to be closer, you might not have destructive interference depending on where the data falls across.
Okay. In theory, yes. So there are two. That's the reason there are two numbers. Okay. The constructive interference guarantees. If you are closer than constructive interference, then you have that guarantee that touching one variable brings the other one into the cache.
How is that? I'm not understanding, because if you happen to be at the end of one cache line and the next one's the beginning of the following cache line,
you have to be aligned on this. You're right. But if you want to take advantage of it, you have to align on this address. On this, you have to do align as on, or just if you're getting memory from malloc, align yourself. You have to be aligned on this number.
So just to conclude, what you're talking about is if you have that number and you make sure that you're skipping by this much, then you're guaranteed not to be. You won't have the problem because you'll go to the beginning of the next cache line.
Yes. So if you want to avoid destructive interference, you put this distance between your two adjacent variables, and regardless of where they are in the cache line, the next one is in another cache line. If you want to play with constructive interference, which means you're actually accessing two variables on the same thread, and you want a free ride on the second one, because locking the first one will lock the entire cache line for you, and accessing the second one, it sees that the cache line is already locked, so it doesn't have to lock it again. That's a constructive interference. In order to do that, you have to be A, closer than this, and B, aligned, like from the beginning, the address of the first variable has to be aligned on this, and from that point forward, you have this many bytes in which you have a guaranteed constructive interference. Yeah?
So loaded cache lines are always aligned at that number?
Beginning of the cache line is aligned on this number, yes. So yeah, the cache lines are, so on x86, both of these numbers are 64, and the cache line begins at address 0 and just goes in 64-byte chunks. It's, as I said, in C++ 17. This is the feature level macro for it. GCC 11 and Clang 13 goes through the else branch. It's in the standard. It's not in either of those compilers. Sorry. Okay, I kind of have to speed up a bit. Anybody curious about the difference between strong and weak exchange? You have a question, or you want to know that? You want to know? Okay, I'll explain. According to the standard, there are two versions of this. One is called strong, one is called weak. For the weak, they say that in addition to whatever the stuff the strong does, which I explained to you previously, the weak exchange can spuriously fail, meaning even if you guess the current value correctly, it can fail to update the atomic with the new X. It will return false and not update. So why would you do that? By the way, on x86, they're exactly the same, which means the weak one never actually fails. So if you guessed correctly, why would you fail? Well, this is what compare and swap does, kind of, in pseudocode. You lock the cache line, you read the value, you compare what you read from memory with your guess, the old value. If you guessed wrong, you update the parameter and you return false. If you guess right, you update the value and return true. The lock there is that hardware lock on the cache line. There is a better way to do it in hardware, which is you read the value, the old value, the current value first, without locking. You don't need a lock to read. Now, if somebody else held the lock, meaning somebody else has modified it, like it won't succeed. But you don't lock exclusive access. You don't get exclusive lock. So you try to get basically the value with essentially with a shared lock, the reader's lock at the hardware level. And if it's wrong, you're done. If it's right, now you get your exclusive lock. Well, maybe while you were putzing around here, somebody changed it. So you have to read again, revalidate again. Could have changed. But if it didn't, then you go and update it. What can happen is you successfully did this part, and then you fail to acquire the lock. On x86, you cannot fail to acquire the lock, meaning once you tell it to acquire the lock, it'll just block forever until it gets the damn lock. Yeah?
You have a title like this right there.
Where?
Should be exchange weak.
Oh, okay, yep. 1-1.
Should that also be compare exchange weak?
Well, that's... Yeah, that's what... Yeah.
Before you spent the time doing the lock.
Well, the advantage is that on some platforms like ARM, you could basically at the hardware level time out on the lock. The hardware itself has that capability to time out on the lock. In which case you would fail to acquire the lock here in certain time. On x86 you just won't time out, you'll wait forever. On ARM it will time out on the lock, and then it just it'll if it times out on the lock, it'll return. Okay, so let me just go to that code that shows the lock with a timeout. Yeah, and this one also should be weak. Okay.
There's also a typo in the variable name. It's OLV instead of OLT.
Oh yeah, I see. Okay, yeah, I see. Okay, so yep, you're right. All here. Okay, so it's a timed lock on ARM, and if it timed out on the lock, it just returned false, even though the old value is actually even though it guessed it correctly. Yeah, in the back.
Just to be very clear, this is not C++. This is just...
This is pseudocode. Yes, this is pseudocode. The lock is a hardware lock, like, and it's on the cache line. It's an exclusive lock on the cache line. Yes.
Yeah, but the weak version only have a benefit if I usually guess wrong. Isn't it like this? If I usually guess right,
Okay.
the wrong version would be faster.
Okay. Yeah. Hold on a second. I'll explain what the benefit is. Yeah, there was another question here.
Yeah, I understand that this is pseudocode, but don't you need some kind of weaker kind of lock to do the comparison?
Well, there is an implied reader's lock on all the reads. Yeah, there is an implied reader's lock on all of this. Yeah. So now the question is, okay, why would you want to do this? Obviously, it's not good for this thread, for the thread that is doing this, because when it fails wrongly, you would just have to loop over, basically retry it. The reason they do this is because it can be on these platforms that can time out on a lock. It can be shown experimentally that it gives you faster throughput overall. Some other threads are getting their work done faster, and the reason has to do with basically how expensive it is to transfer that exclusive lock from one CPU to another. In doing so, in timing out, you're basically saying, I am on a remote CPU versus whoever is currently holding the lock. I'm going to give up and let somebody else try it. And maybe that somebody else is on the same CPU, and they can get that lock with a faster wait. And then when by the time I come back, maybe they'll both give up that lock, so I can then get it on the cheap without long wait and transfer it to my CPU, but without waiting for it. So it's always worse for whoever is doing this, but it's better in aggregate for everybody in case of strong contention. Now remember, you have to volunteer into this, and again, it's compare exchange weak. You have to, if you say strong, the hardware will keep hammering at this lock until it gets it. If you say weak, you are volunteering into it. So you are accepting the fact that your thread may be running slower, and overall, somebody somewhere is running faster and making up for it. Okay, one last thing, because it's interesting. In C++20, they added to the atomic, so works on any type, two operations, wait and notify. Works the same way as a condition. You can wait on any atomic, and you'll block until some other thread notifies you. The interesting thing about it is, so far, everything on atomics has been done on a hardware level. This one isn't. This involves a system call. There is a futex usually underneath.
Question about this.
Yeah.
Is this susceptible to spurious?
Yes. Okay. No, this one isn't. So it's kind of so it can spuriously wake up, but it will put itself back to sleep. So you basically the wake up is possible, but inside the wait, it's going to recompare. It's also comparing with the value you want to change. It will recompare the value and put itself back to sleep. All right. One other thing that we haven't covered and we need to cover has to do with this. Let's look at this Q. Here is my atomic, which is the index into this array. And this is what I do to push my data into the queue. First of all, I reserve my exclusive slot in the array, not available to anybody. Why is it not available to anybody? Because I'm doing atomic add, which means if I get, let's say, the value of 0 from here, no other thread could have seen the value of 0. If somebody else comes with the same fetch add at the same time, either they will see 0, then I won't, or I will see 0, then they won't. That's the atomicity guarantee. So if I get back 0, I know that nobody else has access to the array element 0. I then assign to Q sub 0 some value. Question is this enough? Well, the problem is front is atomic. So for the front, I have this atomicity guarantee. Q is just a plain old integer. In general, I have no guarantees that my thread writing into this Q sub 0, that value becomes visible to any other threads at any time. In general. So on x86, yes, it does. On ARM, it doesn't become visible for some time. Basically, until the hardware decides to flush the caches and write the content of the cache back into main memory, what I did doesn't become visible. So yes, I got my exclusive slot. Nobody can write into it, but nobody can read from it either, because nobody knows when I'm done modifying it. So the same thing with the compare and swap. So okay, let's keep that slide for time. So here is a kind of much more generic version of it. This is a very common thing. It's called a publishing protocol. I have an atomic pointer to a memory location. I want to publish a new piece of data in a concurrent system to everybody. What I do is first I prepare the data, but I don't publish my value yet. I don't update this pointer. So I prepare the data like here and here. No other thread can gain access to it because there are no shared pointers pointing to them. My thread is the only one that knows about these memory locations. When I'm done preparing the data, I do atomically retarget the pointer. And now anybody who goes through this pointer can access this, suddenly becomes visible, reachable through this pointer. Okay, that's good. What guarantees do I have? I have a guarantee that this pointer doesn't change before I finish preparing my data. But what guarantees do I have that the other thread can actually see what I've done here? None. Because the rest of the memory is not atomic. Only the pointer is atomic. So here is my problem. One CPU updated some non-atomic memory, changed it. The result sits in cache. The other CPU updated some non-atomic memory, changed it. The result sits in cache. Main memory hasn't changed yet. It's non-atomic, and there's no guarantees about visibility on non-atomic changes. Okay, so okay, I'll have to speed up a bit. How do I actually make it work? The second half of atomics and the second half of the memory model is what's called memory barriers or memory order, same thing, different language. I can choose to associate a memory barrier with an atomic operation. And the memory barriers are these things that guarantee visibility of other memory updates, not just the atomic, but all other memory that I have updated. This is also a hardware thing. It's provided by the hardware. It's basically like a flush. So without the memory barriers, here is my atomic. One thread sees me change the value of the atomic variable. So this thread is changing it. This thread is watching it. This thread has changed some other values, non-atomic here. This thread hasn't seen that value change yet. It will only see it here, no guarantees. The interesting types are basically two types of barriers. There is an acquire barrier, a memory barrier, or the acquire order. It says that all operations that in program order happens after the barrier become visible after the barrier. And of course, there is a release barrier. So let's go to release. Says the other thing, that everything that was done, every memory read and write, and we're interested about, in our publishing protocol, we care about writes. So let's go back to the publishing protocol just so to illustrate the. I'm preparing that. I'm writing into that. And then I'm going to atomically to update my pointer. If I do that not just atomically, but with the release barrier, I'll have a guarantee that all the writes that were done in program order before the release barrier will become visible to any other thread that observes this change in atomic pointer. As long as they must participate in that guarantee. So they must issue an acquire barrier because they need the opposite guarantee. They need the guarantee that anything that they do after the atomic barrier reflects the visibility that was before. So I'm releasing it with the release barrier. I'm updating the pointer with the release barrier, forcing the visibility of everything I have done before the release. The other thread acquires the pointer or reads it with acquire barrier, guaranteeing that everything it does after acquisition sees the state of the memory at least how it was when the atomic pointer changed. It could see more, but it can't not see those updates that happened before. So these are bidirectional barriers. And of course, if there are bidirectional barriers, there is also the. So this is basically what I just described. If there are half barriers, there is a full barrier. You can take a full barrier that embeds guarantees of both. So it's both acquire and release. It guarantees both that everything you have written becomes visible to everybody else, and everything that everybody else has written becomes visible to you at the same time. The bidirectional barrier. So now we can finally see how the locks actually work. So here is your lock. What does it do? Well, in order to lock the lock, so let's say this L is actually an atomic value, starts its life with 0. In order to lock the lock, you store a 1 into it. Well, storing 1 would just grab you the lock, even if somebody else already held the lock. So that's no good. In reality, what you do is you exchange it with 1. And if you get back 1, you exchanged 1 with 1, so you haven't really changed it. But you know that somebody else held it. You sit there in a while loop. If you got back 0, you know that nobody held it. Now, and you know that it changed with 1, which means everybody else can't proceed through that lock. So now you have your exclusive access. But that's not enough, because we still have no guarantees about that X. You have to do this, put the barrier of the memory order acquire, which means anything that you do after the barrier is guaranteed to see the memory state how it was when you did that atomic operation. So whatever changes somebody else did before, they become visible to you, guaranteed. And then when you want to give up, now you can just store 0 because you know exactly what it has. It definitely has 1. You don't need to check that. So you just store 0, but not just store 0. Store 0 unlocks the lock. You release, you put the memory order release, which guarantees that all the changes you made here will become visible to anybody else who acquires the lock after you. That thing in the middle is the critical section. No code can leave the critical section. Code can enter critical section. So when I said after you did the acquire, you are guaranteed to see the memory state at least how it was at the moment when you read the atomic. You can see the later state of the memory. You just can't see the earlier state. You can't not see what was done outside of the critical section. Now, why is it not a problem that you can see the later state? What if somebody else comes in and changes X? You don't want to see that. Well, that cannot happen as long as everybody takes the lock to access X, because they are prevented from changing it by exclusion, by the value of the flag. So in here, I have a guarantee that whatever somebody else did to X before this point, I will see. And nobody else is doing anything to X if they're correctly using the lock. If there is one other thread somewhere that accesses X without taking the lock, all bets are off, and your program has undefined behavior. So that's why when I say, for example, the release barrier makes the value visible to all other threads, I'm very carefully saying only to those who do their half of the work and issue the acquire barrier. If you don't issue the acquire barrier, there are no guarantees about what you get. Okay, let's skip a little bit. The memory order argument goes on to all of those functions like load and fetch. So load can take the memory order argument. There is a slight wrinkle in all of this. According to the C++ standard, load cannot use memory order release. It will compile. It's just undefined behavior. Store cannot use acquire. Same thing, it will compile, and it's undefined behavior.
Does it need to compile? Could they be different types?
Well, it says undefined, there are different types. It says undefined behavior, not the program is ill-formed.
That's terrible.
In the standard, they say undefined behavior. Now, a compiler, so because they don't say a program is ill-formed, the compiler cannot issue a hard error, it could issue a warning. But it doesn't say the program is ill-formed, it says it's undefined behavior. Now, acquire store is actually useful. Ticket locks use that. So you have to use exchange instead of store, and you discard the result. You're just doing exchange for its store effect, because exchange can have acquire or bidirectional barrier. Okay, now here comes another reason to not use overloaded operators. The highest order in the C++ memory model is this one, sequential consistency. Not only it guarantees it gives you acquire release barriers on every atomic access, it also guarantees a single order of execution of atomic operations on different atomic variables. Incidentally, it's the most expensive one to do. This implicitly uses that order, always. It definitely makes your life much easier. You don't need to think about issuing correct memory barriers. It also makes your code slower. Given how fast good spin locks can be, I would say that, okay, if this is good enough for you, still don't use it. Use spin lock. It's easier to reason about than atomics, even with a full barrier. If you need to push the performance beyond the spin lock, you have to take control of memory order explicitly and use these. The other reason is we don't just write code for computers. We write it for other people. Okay, so I'll skip the performance stuff. Okay, we write it for other people. The memory order argument actually explains what you want to do. When you write this, you're saying that this number is not used as an index or offset or a pointer into any other data. Because if it were, it would be the wrong barrier. You would want to release it or acquire it. This is just a count by itself. No other memory depends on it. That's why you didn't put any memory order. This is a release. You're indexing with that value into some array or something like that, and you're guaranteeing that whatever you're indexing into has been updated at this point. Like this. You finished updating the value, and then you did the release. And when I see the release, I know that there is a dependent data somewhere that you have just made public. This, I don't know what you mean. Okay, so one case where your intent is not easy to express, and that's because we don't have non-atomic operations on atomics. This is the constructor. I have an atomic, but I can't, for some reason, the initialization is complex, and I can't initialize it on a member initialization list in one shot. Why am I doing atomic operations in the constructor? By definition, in the constructor, only one thread can see the object. It hasn't been constructed yet. Nobody else knows that it's there. And so what am I protecting against? Well, I'm not protecting against anybody. I just can't do anything else. Well, I can use atomic init and atomic ref, but...
Could you do that non-atomically and then store the result of the atomic?
You can, but again, why are you storing atomically?
Well, because you have to.
Because you have to, yes, exactly. Okay, so atomics basically are your memory model made visible. They are not always fastest, but they can make your code significantly faster. And usually, if you want to make your code significantly faster, you have to take explicit control of the memory barriers. Otherwise, good locks would get you there. And every time we're talking about performance, you have to measure it. Questions on atomics? Yeah.
I didn't understand the last slide with the constructor. Why are you doing ++?
I'm just computing, that's just how I'm computing the value of that. I can't, for whatever reason, I cannot initialize the atomic with a single value. I have to compute, let's say my atomic will be initialized with a number of even values in some vector that is given to me. So I'm looping over the vector and counting the even values. And that should be what goes into atomic at the point of construction. Okay, well, let's defer the remaining questions and go into parallel STL. I'll speed up a bit. Parallel STL, C++ 17. Okay, we've seen shared mutex. We've seen the destructive interference side. The big one, parallel algorithms. For not all, but a lot of algorithms, where this is some algorithm, there is a version where there is a new first argument. And the first argument is execution policy, and these are your choices. This one was added in 20. Looks like this. So you had this before. You change it to that. And it magically became parallel. It can now execute in parallel. Can. Doesn't have to. All right, so, well, how do you get it? You need the compiler. Obviously, that is capable of C++17. You need to enable C++17. And what we're used to is you compile and run it. No. This is the first time that I've seen that the compilers are not self-sufficient. For x86, you need to get the thread building blocks thingy. Okay, fine, that doesn't sound so bad. Actually, you need to get the right version of the thread building blocks. And by the way, GCC 10, for example, would not compile with the same version as GCC 11. And getting the latest one doesn't necessarily make it right for everybody. Right at this current moment, GCC 11 and the latest TBB are the matched pair. When I first tried it was when GCC 9 was the latest compiler. The latest TBB wasn't the right one. You had to get one before.
Quick comment. MSVC works out of the library, so you don't need TBB for it.
Okay. Since I never used it, so I just don't know. But Clang, same way. Clang, by the way, just uses GCC's version of parallel STL. Okay, once you get precisely the right version of TBB, it will work. Well, let's see how well it works. No. So, for each without parallel policy. For each with sequential policy, right here.
What does that mean? Sequential policy versus just none?
Well, okay, in practice it means exactly the same thing. You can pass that argument in probably. I mean, it means everything will be executed exactly in sequence, which is what it does without it. I suspect it's there, so you can basically write generic code with the 4 arguments, and you have something to pass in if you don't want parallelism. Parallel policy, yeah, question?
When you said it doesn't work, is that a compilation error or a linker error?
Which one?
With the TDD.
Oh, usually you get compilation error. There was actually one case that I have seen between GCC 10 and one particular version of TDD, thread build TBB, where you got a linker error. It compiled and then the signatures didn't match. So usually you get compilation error on the headers, and they were not merciful. There was, as I said, once I got a linker error. Okay, parallel policy. Well, there is also this parallel sequence that I'll talk about in a moment. Okay, let's run. Okay, I didn't turn. Okay, ignore the threads number. It's always running on one main thread. It's doing its own threading. So there is one main thread, and then I'm telling it to execute with the parallel policy, which means it has its own internal parallelism, which Google Benchmark knows nothing about. So parallel for each. On the size of vector is only 1024. Parallel for each with 32K elements, 1 million elements, 4 million elements. Sequential for each with the same numbers. So as you can see, doing parallel for each on a vector of 1024 doesn't do you any good. Above that, it's actually pretty good. 8x is the most you can realistically expect on this machine. It has SMT, but it's on this processor it's not very effective. Realistically, 8x is about the most you can expect. Yes.
I would say that for each isn't the poster child not the best algorithm because they're different, right? The parallel overload doesn't return anything, whereas the non-execution policy overload will return the function. It's defined.
But this is the one with this is the same overload. This is just the one with.
Sure. But the overload without the execution policy.
Yeah, but that's not the one I'm benchmarking.
Sure, but I'm saying that the parallel for each is not a drop-in replacement.
Oh, okay. So, yeah, it's not a drop-in replacement. Well, the one without policy is because you can always discard the result.
Yeah, but for each is one of the few algorithms that's actually specified to do things in order in the non-execution policy version.
Yeah, and we'll yes, but so the one without the policy is a drop-in replacement for the one with the policy, but not the other way around. Yeah. But here I'm actually comparing the same one. This is the one with sequential policy.
Oh, yeah.
So give it enough data, and it's spectacularly effective. What's enough data depends on the algorithm and the data, how much computation you do.
Does it actually create, I mean, if you did a look for the thread ID inside that for each, would you get different thread IDs? Yeah.
I haven't tried, we can try. It doesn't create like your normal P threads, but it may still have a different thread ID. Now,
Not one for every individual loop, but there will be some number of different threads that you'll see.
yeah, I don't think they're P threads, but I think they do it at a lower level, but they are threads, so we can try that.
Is it using like regular threads under the hood, or it's using some special?
It's
That would be a TBB.
yeah, it would be a TBB thing, and there is a reason it's Intel TBB. They are friendlier with the hardware than anybody else. So I'm not sure what they're using. Not all algorithms scale equally well. So for example, this is a copy, and if you do this, it doesn't scale at all. And the reason is that the last thing is an output iterator.
Is this even permitted?
Yeah, compiles perfectly.
It does not run.
No, it runs, but it runs sequentially. It executes. It executes, but it just runs sequentially.
But you have unprotected. You're modifying the vector. That inserter is modifying the vector without synchronization.
Okay, so it may, I don't know if it may be UB or not, I don't know.
It's
It's UB? Okay, so it may be UB. I know that part, at least like in GCC and Clang, that particular overload just, so their implementation detects what you're doing, and they dispatch into a different overload if you can actually do it in parallel. Yes?
Can I control somehow the number of threads that I use?
No. Okay, so if you have a pre-allocated vector and you give it a regular vector like random access iterator masquerading as an output iterator, then it scales.
So Fedor, what you're saying is that the copy looks into the category of the last.
The actual implementation, yes, it does.
Is correct.
Yes, yes. Okay, so yeah.
How does that work? So even if you request par, it doesn't have to, right?
It absolutely doesn't have to give you anything parallel. And in particular, the way this is done is they have a special implementation in which they actually look inside vector, they reach inside vector, and they're doing it actually in chunks. So the parallel implementation of it actually, is basically embedded into the vector. They get more access to the vector. In order to be efficient, they chunk it and they get they're reaching directly into the vector, and that's what allows them to be so efficient. But when they decide whether to call the parallel or sequential implementation, they look at what the iterators are.
So you're saying that this would have done this for sequential.
No, it doesn't. It does not update the size.
Constructor you call.
The The size was set in the constructor.
So you're
You've created the elements, and then you're overwriting.
Okay, let's push forward and we'll come back to that like in the break unofficially. So you have no control over how many threads, what do they do. In particular, if you run your own threads on top of these, you typically don't get any more scaling from it because every one of them saturates the CPU as well as it can. So this isn't a substitute for executors, but it's something. Okay, let's skip on sequence policy. Okay. I want to briefly talk about coroutines. C++ 20. Yeah, JThread, thread cancellation made its appearance. For the first time, there is a standard compliant way to do thread cancellation. Okay. Well, yeah, but I mean, that's what you have to do to be to be standard compliant. I'm not going to cover that. If you want to read that, go to CppNow and see how they do cancellation. Atomic weight was added. I covered it. This is a big one, the coroutines. What are the coroutines? Very simple. Coroutines are functions that can be interrupted and resumed. In general, there are two types of coroutines. Stackful, that's where they're like normal functions. They have their own stack. Sometimes they're called fibers. Powerful, flexible, pain to implement. Stackless, they don't have their own stack. I'll show you what they have. That's what we got. Stackless coroutines are what we got. So here is your normal function. Has a stack. I'm calling another function. Add it onto the stack. Now here is a coroutine. What makes it coroutine a coroutine? Actually, nothing so far. We'll see. I'll show you what actually makes it a coroutine. So before I can use the coroutine, I need to create this object called coroutine handle. It's a template. I'll show you what goes inside. So for now, there is some magic object called coroutine handle. Coroutine handle is basically like a smart pointer. It points to some memory allocated on the heap that is called activation frame. So let's see what goes in. So now I have my function f, in which I have my coroutine handle, and I call this function coroutine. Name isn't magic, that's just what I called. This coroutine can be suspended. While it's just after I call it, it does have a little bit of stack state. It has the return address and the suspension point where it would resume. Now the coroutine calls another function. You can do that. Except at this point, you lost the ability to suspend it because now you have that stack state right here that knows nothing about any coroutine stuff. This is just a regular function with a regular stack. That's the price you pay for stackless coroutines. You can only suspend them from the top level of the coroutine. Once they start calling functions, regular functions, they can no longer be suspended. Okay, so basically that's the difference. All right, let's go back to the stack. So our function g finished, exited, and now we're back to, so the stack of the coroutine got turned down. This disappeared. The stack of g got turned down. We're back to here, and we could suspend it because we're back to the top level. What would happen if we suspended it? If we suspended it, the bits of state that were on the stack are copied into the activation frame, and the control returns to the caller. The caller has the coroutine handle, which is a pointer to the activation frame. The caller keeps running. The activation frame sits there. The coroutine is not running. Let's say the caller invokes operator paren on the handle and the caller invokes another function, h, first. It goes on the stack. There is no coroutine stack anywhere here. A normal function, so everything is normal. The caller then, or maybe that function h, anybody, calls resume method on the coroutine handle. At that point, the activation frame is accessed through the handle. The stack bits that are necessary are reconstructed, specifically the return address is what's necessary, reconstructed from the coroutine frame, and coroutine starts running. So I called coro from f, it suspended itself, f kept running, f called h, and now h resumed. So now effectively my coro is like a child of h, not at f. The order of the stack. Stack of coro was sitting right on top of f, and now it sits right on top of h. So it looks from this point that the caller of coro is h now, if you look at the stack, not f anymore. If the coroutine finishes, it just tears down the stack. Activation frame will be turned down when the coroutine handle disappears. So functions that can suspend themselves. Suspending is explicit. It's cooperative multitasking. Nobody can force you to suspend it. The coroutine has to suspend itself. It's impossible to come in from the outside and say, suspend now. No, it has to suspend itself. Functions have stack frames, coroutines have handle objects. The lifetime of the coroutine is the lifetime of that handle. The resume can be anywhere. The resume actually can be from different thread that, if I have time, I'll show you. That's actually pretty cool. You can transfer the location of the caller from one thread to another. How do you get them first? Well, all the C++20 compliant versions of the compilers have them. GCC2 requires an additional switch. Clang requires an additional switch, which is not quite the same. You must be using the libc++, not the default libstd++. And in Clang, it lives still at least up to Clang 13. Don't know about 14. It lives in experimental coroutine header and std experimental namespace, as opposed to std and coroutine. In Visual Studio, I haven't tried it myself, but I read that you don't need anything other than C++20 and the coroutine header. There is nothing special to declare a coroutine. There is no special function to it. All right, we're almost out of time. Let me show you that, because I'll show you just one example how they jump threads. Sorry, because that's a really cool thing to see. Okay, main thread. I'm creating threads, but the default constructor of the thread. The default constructing a thread doesn't make anything run. Creates a thread object that doesn't actually have any code to execute and doesn't create any threads. But you can assign to it. Invokes this function coro. Passes two threads by reference and some number. Prints something, except main thread isn't really done because these J threads join, therefore they block in the destructor. Of course, they would only block if I actually assigned to it. So right now, if I don't do anything to it like this, it doesn't have any code to run, so it won't block. But if I assign another thread object to it that is running, then it will block on the destructor. And when the destructor is unblocked, that's when it's really done. Okay, coro. I'll print when it starts, and this is a way to, this co-await operator is how you suspend the coroutine. As I say, it has to suspend from itself. It has to do this. Nobody else can do it for you. It returns some object that is a big boilerplate type that don't want to look at. At this point, it will be suspended. If it resumes from this moment, right here. And it'll print again. And then we can suspend it again. And then we can print again. And you can do it more than once if you want. Okay, so that's the coroutine. Now here comes the interesting part. It returns this object awaitable. And the name isn't magic. You can call it anything. What is magic is it must have this member functions. It must have these member functions. If it doesn't have them, something somewhere won't compile. The error messages you get are actually surprisingly readable. The compiler actually tells you, I need an await resume. If you didn't put it. Okay. Compiler calls all of these. You don't call them explicitly. Compiler calls them. In particular, when you suspend, await suspend gets called. Compiler passes it the coroutine handle. You don't. You don't call it. The compiler actually calls it. Now, watch what I'm doing. Okay, where is the constructor? Constructor. Oh, right. Okay, when I constructed it, I passed a thread into it, bounded by reference. At this moment here, I'm going to create a new thread with code to run this time and assign it to this, which is just a reference to that T3, which came from the constructor. And the constructor is the only thing that I do call from Coro right here. So one of these two threads that I passed in that I default constructed in the main, this T1, passed by reference in here into awaitable, gets bound to the reference inside the awaitable, gets assigned to this, gets assigned a real thread finally that is running, and now that the thing that was T1 in the main now has a real code and a real thread associated with it, and now we're running, and what we're executing is the resume, and H is the coroutine handle. Now here is the interesting bit on this. The coroutine will resume while you're inside of this. This leads to some very interesting race conditions inside this function. Happens very fast, but let's see what happened. Main thread, its ID. Coroutine runs on the main thread. I didn't start into it. I just called coroutine from the main thread. So far, so good. Awaitable is constructed on the coroutine constructed awaitable. Same thread. Nothing. There are no other threads at this point. New thread ID. That's the one. That's happening where I created a new unnamed. Remember the unnamed thread. Yep. Well, it wasn't T. Oh, sorry. It will become T3 like a fraction of a nanosecond later. So this is the unnamed thread, which is going to become T3. By the time the print completed, yeah, it probably is already T3, but that's the origin of this object. So new thread. Now main thread, by the way, main thread is done like calling it. Why so late? That's I have to put mutexes on cout, so that's just when it got its turn to print stuff. So somewhere in here, main thread, quote unquote done, except it's blocked on the destructors now. Okay, awaitable will eventually get destroyed. That part is not particularly interesting. But that thread, new thread, with ID ending on 648, the only code that it has in there is hresume. So now I resume the coroutine. These two prints are from the same function. Again, coroutine. Coroutine. Coroutine started, suspended, resumed. Here are these three statements. It's the same function. Coroutine resumed, coroutine started on 808. Coroutine resumed on 648. That function is now running on a different thread. And the same thing again I'll do with T2. At the end, the destructors of T1 and T2 block, and then when the threads are done, then block, and the main thread is really done. So I had this function, this one function, that was executed on one thread, on another thread, and on a third thread. And by the way, this I is a local variable. inside it's passed by value. So inside that function is a local variable. It's normally would be allocated on the stack, and it is. Same value. That value of I, that local variable, followed the thread as the coroutine went with it. So it's local. It's not global. It's not like shared between threads. But like this coroutine stuff, the way they copy in and out of activation frame, makes your entire stack. Yeah, in this case, my stack is trivial. I have one local variable. 110 doesn't make any difference. My local variables are following the thread as the function moves. Looks really cool. So really hard to understand. And when I wrote the slide, I didn't know that there is another much bigger presentation on coroutines, so I'll attend that one. The thing they did with the standard is they provided a framework for coroutines. You're not really expected to write the code that I wrote. There are coroutine libraries that have this awaitable type that I have shown you, because it's boilerplate. The standard says you must have like await notify, await return, and all of this. Why would you, if you have to write this every time, why would you like write it by hand every time? Obviously, you would create a library because there is nothing else that you could put there. Anything else you try to do with it, compiler will reject. For some of them, this is like a simple one. There are a few more complex things you could do with it. Compiler, the standard goes into such details, like it specifies that some of them must be no except. Again, you get surprisingly good errors. Function such and such is required and must be no except. That's what both Clang and GCC tell you. Not bad. So there is lots of libraries. The reason I'm not showing you any is because I don't think there is a dominant one at this point. So pick the one you like, but like I don't think it's so fresh that I don't think sort of the common, like if you wish the patterns, the commonly accepted solutions, classic definition of pattern, commonly accepted solutions to frequently occurring problems. I don't think that emerged yet. So either write your own or for your application-specific task, or use one of their own. Never write this raw C++ stuff again. Use a library. Okay, so by the way, the other common example for coroutines is this lazy generator. So this whole thing, that's it. That's the whole coroutine. There is a co-yield is a shorter form of co-await with certain restrictions. Infinite loop, but within the loop it suspends itself every time. And every time you resume it, it'll plus the I and return the value. So every time you call it, you get the next I, but it's computed lazily when you call it. And when you don't call it, it sits there suspended and not doing anything. So lazy generator. If you put like I less than 10 here, then the generator will have limit. After you call it 10 times, it will exit, and then it's undefined behavior. If you try to resume it, you must destroy the handle at that point. If you don't put a limit, it'll keep giving you new stuff until you destroy the handle yourself. If you destroy the handle, that's it. You just destroy that function. Okay, so yeah, I'm not going to show you the standard types. So the coroutine handle is the main thing you need to do to invoke it, and it's basically a smart pointer to the activation frame. You destroy the handle, activation frame goes away. As long as you have the activation frame, you can call resume on it. Okay, there are lots of boilerplate and explanation for what they all do, which actually isn't particularly important. Okay, we'll skip that because we're out of time. If the coroutine exits, or if you destroy the handle, that's the end of the coroutine. Either of those two things happen, you cannot resume it anymore. There is a coroutine, so if it falls through the bottom, it returns. Or you can call coreturn. You cannot call return. So basically, if you put, now, what makes a coroutine? This. So if you have this, co-yield or co-await, it's a coroutine, and then you're not allowed to use return. Then you must use coreturn. You can still fall through the bottom, and If it's a coroutine, then falling through the bottom is an implicit co-return, not implicit return. So either you either implicitly or explicitly call co-return, and that ends the coroutine. And then you can't resume it. How do you know that you can't resume it? There is this done flag on the handle, which will be set, and then you know that you shouldn't call resume. That's UB. If it never returns, like if you remove this part, make it an infinite loop, then it never returns. Then you just delete the handle when you're done with it.
Quick question.
Yeah.
So theoretically, you could mark a coroutine no return?
No. Return types of return types of coroutines are standardized. There is a ton of boilerplate requirements on what must be in that return type. So they have to return something. The object can have any name. The generator isn't a standard name, but what goes inside the generator? Let's see, where is it?
If you have object that has any type structure, when you destroy the handler, are the destructors called?
The coroutine isn't running, and it's you mean if there are objects on the stack space? I think so, but we can easily test. But I think so. We can test it in right after the class. I think they have to, but we'll test that. Okay, so just because you asked, the name is whatever you want. Doesn't have to be a template. Everything here, this must be typed in like that, verbatim. Promise underscore type. If you don't do it, something somewhere will not compile, and the compiler tell you that your return type, whatever it is, has to have a thing called promise type in it, nested type. Could be a using alias. So it doesn't have to be a nested class, could be a using alias or something, but it has to have a nested type. Inside that nested type, you must have initial suspend, final suspend with no except. Initial suspend can be no except, but doesn't have to be. Unhandled exception, must return void, and so on and so forth. All of these are standardized. So no, it cannot be no return. Furthermore, it's a very specific return. Again, write this between 0 and 1 time. If you get a library, it's 0. If you write your own, it's 1. No more than that. Okay, and we're out of time. So let's get to okay, we did the live demo of this thread. Compiler support, kind of cutting edge. Lots of boilerplate code, don't write it more than once. Use libraries. This is really cool stuff. We're absolutely certain that they're very useful. We're not absolutely certain what for. Probably work stealing and lazy execution. I mean, we know that they're useful for work stealing. It's pretty much the only way, not necessarily doing the coroutines in C++20. People have been doing work stealing before that, but something like that is basically what work stealing does. So it gives you kind of an easier way to do work stealing. Probably useful for other things. We don't quite know what. All right. I'll put up the final slide with questions, and we can ask questions about anything. Yeah. No, this is parallel STL, sorry. Yeah, save. Come on. So we've seen coroutines, which is like the latest of the concurrency-related features, evolution of the standard. I've tried to show you kind of how to use them, why to use them, and why they're there. If you want to read more, I do write especially in my book on the performance, about a lot of the concurrency stuff. And with that, thank you for being patient.